Okay, we now reach the practical part of our video session, which is session 6. In the practical part, we want to practically design the module that we were talking about, and then we want to test our module on the real hardware. For today's test, I have the Z board here with me, and for the kind of module that we are going to design, the Z board is enough, and it's not really different if you use the Z board or the ZC706 or ZC702 or any other ZYNQ board for this test. So what I want to do is, first I want to create the IP component that I was talking about in the presentation, and then I will use that IP component in another Vivado project, and I will connect the IP component to the ZYNQ PS. Let's first once more review the functionality that our IP component should have. Here is one of the slides that I showed you during the presentation. What I basically want to do, I want to create a hardware accelerator that receives an array of zeros and ones, in fact an array of numbers, and it searches for user-defined patterns inside this array and counts how many times this specific pattern has occurred in the received data. So what I want my hardware accelerator to be able to do is that I want my hardware accelerator to be able to receive these chunks of data one by one. For each chunk of data, I want my hardware accelerator to be able to tell me how many number of times a specific pattern has happened. My hardware accelerator should also be able to accept the pattern itself. So there should be an interface through which the CPU first sets the pattern, then the CPU sends the chunks of data, and then my hardware accelerator should be able to tell the CPU that for each chunk of data, how many times a specific pattern has happened, and then it also should be able to tell the CPU in total how many times that specific pattern has happened. I want my hardware accelerator to be able to do this operation as fast as possible. And as I will show you, my hardware accelerator will be able for each chunk of data to count occurrences of the specific pattern in just one clock cycle. Now imagine if you want to do the same thing with the CPU. I mean, instead of passing the data to the hardware accelerator, imagine you want to write a software which is running on the CPU and is responsible for counting how many times a specific pattern has occurred. Even with the most optimized software that you develop for your CPU, for each chunk of data, it takes a very long time. It takes hundreds of clock cycles for each chunk of data for you, in fact, to count number of occurrences of a special pattern. And this is an advantage of hardware accelerators. In fact, since the hardware is specialized for performing the special operation that I want, it done that specific task very fast and in much smaller amount of time. Okay, so my hardware accelerator has one enable signal, which is basically going from entering the FPGA from outside. And this enable signal, when it is active, then the hardware accelerator will produce a signal, in fact, an indicator to the outside world if number of occurrences of a specific pattern is above a threshold. So my hardware accelerator receives a threshold value from the CPU. It receives the pattern from the CPU. It receives the data from the CPU. Then in the data, it searches for that specific pattern and it counts how many number of times that specific pattern has occurred. If the number of times that the specific pattern has occurred is above the threshold and the enabled signal is active, then my hardware accelerator will activate the signal to the outside. Otherwise, the signal will be 0. Furthermore, after the hardware accelerator, in fact, received all of the data and counted number of occurrences of the specific pattern in the data, it produces an interrupt to the CPU to inform the CPU that I have done my task, you can come and grab the results. So these are the functionalities that I want to implement in my hardware accelerator. For now, to make the problem simple, I say that total number of chunks of data that we receive each time the hardware accelerator processes each time is limited to 32. So each time it will practically receive 32 chunks of data. For each chunk of data, it searches for the occurrences of the pattern, it counts total occurrences, it counts per chunk occurrences, and based on that, it generates the signal and the interrupt. Here is a simple representation of how I'm going to implement this hardware. My hardware, I have decided to include 2 AXI slave plugs in my hardware. I want to use one AXI slave light plug in my hardware for interfacing to the CPU, for generating the interrupt, for receiving the enable and producing the signal, and for reporting total number of chunks that we have found to the CPU. And I want to use an AXI slave full plug with burst capability actually to receive the data from the CPU. Inside my AXI slave full block, I will have a memory, a small memory, which is responsible for storing the incoming data, and then another small memory, which is responsible for storing number of occurrences of the pattern in each piece of data that we have received. Our pattern finder engine will be also implemented in our AXI slave full block. Okay, let's go and begin with the design of the hardware. Here I have the Vivado environment and I have just created an empty project for my Z board. Now what I do, I begin a new IP component. So I come to the tools folder and then I begin with create and package IP. But wait a moment, before that my suggestion is you begin with project settings. Come to project settings and then look at the general tab and make sure that all of the configuration here is compatible with what you want. If this is true, you can begin with, in fact, create and package IP wizard. So I open the create and package IP wizard, I press next, and I select create a new AXI for peripheral, and then here I can in fact define a name for my new IP that I am creating and some description for the IP and its location and information like that. And then when I press next, I come to the interface, in fact to the dialog box through which I can define how many AXI plugs is my IP going to have and what type of AXI plugs are included in my IP. For my specific IP, as I told you, I want to have two AXI slave plugs. One of them, I want it to be a simple AXI slave light. The other one, I want to have, in fact, a full AXI slave interface. And the data bits for both of them, for now, I want to be 32 bits. And for, in fact, my AXI slave full plug, I want to have a memory of size 64 inside my component. Now, I press next and I press finish. What happens is that now if I come to IP catalog and I search for my IP, I can see that the IP that we have just created is added to the list of available IPs in the Vivado. The next step is I should go and do a little bit of RTL coding. In fact, Vivado has already generated for me a very big portion of the RTL that I need. Vivado has already generated for me all of the logic that I need for talking to the AXI. It has also generated for me the memory block that I need to store the incoming data. So I want to have a look at the generated HDL core for my IP. So what I do, I right-click on my IP, and then I select Edit in IP Packager. A new project opens as I select Edit in IP Packager. And inside this project, you will have the source code that is generated for your IP automatically by the Vivado environment. Now, if I select the top level component, which is called my IP, actually if I go through the HDL code, what I see is instantiation of two AXI plugs. The first AXI plug is basically an AXI slave light. This is obvious as you see the limited number of AXI slave ports that this plug has. As I told you during the presentation, the AXI slave light is a simplified version of AXI slave foo that doesn't support bursts. As a result, the number of signals that we need to implement this interface are very limited. The second component that I see here is, in fact, the AXI slave full plug that we have and we are going to use for our design. As you see here, the number of AXI signals that we have here are much more. This is because this AXI slave plug is going to implement a full AXI slave interface with support for bursts. So it needs all of those signals which are required for handling the burst transfers. So it needs all of those signals which are required for handling the burst transfers. Now, if I open these two IP components, I can see an example implementation of an AXI slave light block, and the other one an example implementation of an AXI slave full plug in Verilog RTL. The message here is that when you are designing, when you are creating your own IP with Vivado environment and through the procedure that I showed you, you practically don't need to implement the AXI plug itself. As I show you what I want to do, in order to add the functionality that I want to this module, what I do is just I make simple addition to the code and simple modifications. And that is all what I do. Okay. Now, to proceed, I need first the pattern search engine. And that is a piece of RTL which receives the chunk of data, which receives the pattern and counts how many number of times this pattern has happened in this chunk of data. That one I should implement in RTL completely myself. I have previously done that and I show you my implementation. Here is the code that I have written for counting number of occurrences of a pattern in an incoming, in fact, a stream of data bits. I have called it count number of patterns. It's a module implemented in system Verilog. It has 2 input ports and 1 output port. In is the port through which the chunk of data enters. Pattern is the pattern for which the search should happen. And count out is the number of occurrences of pattern inside in. All of the widths values for these 3 ports are parameters. Obviously, for count out, the parameter value is a function of the width of the in value. Okay, so I have considered a kind of upper limit, upper possible limit for the width of the count out. Now, the actual implementation is very simple and straightforward. I have a simple for loop, and practically this for loop, when synthesized, it turns into several instantiation of a fixed pattern comparison hardware for each bit of the incoming, in fact, data stream. So what is happening is that always I'm comparing the input with the pattern, and I am incrementing the count out by 1 if an equivalent, in fact, pattern is found. The entire circuit that you see here is practically a combinational circuit. There are no flip-flops, there is no delay, and as the signals enter this module, with obviously the delay of the logic and gates that we have inside this module, the output will be generated. So I expect everything happens, in fact, without using a clock signal. This is a completely combinational circuit. So for this circuit performs the search that I need, and what I need to do, I need to instantiate this circuit in my AXI slave full interface. Okay, now for the modifications that I need to make in the AXI slave light interface and AXI slave full interface, I have done them before, and I just give you hints of what modifications I should make, and then I show you actually the code that I have written. So, first step, the count number of pattern module, this file which I have, it should be added to the list of HTML files that I use for my IP. So I copy this file into the folder which is responsible for keeping the source RTL of my IP. Now I have this file here, and obviously inside my Vivado project I need to add. Now I have this file in my folder, and obviously in my Vivado project I need to add also this file to the source, to the list of the files which are included for this IP component. So I add files, and then I find my file, and then I add it here to the list of files for the project. Now I need to instantiate this module inside my AXI slave full block. I have done that before, and I show you the instantiated module inside the AXI slave full block. So here I have opened the modified AXI slave full block, and if I come down, I can find a section in the automatically generated RTL is beginning with add user logic here and is ending with user logic ends. And I will always try to add my modifications to the design between these two sections. But sometimes it's required that you also modify other parts of the RTL. Okay, so the first step I take is that I add my pattern counting engine into the RTL of AXI full block. And now, obviously, the input port to my pattern counting engine will be the write data port of AXI slave block. In fact, I want, as the CPU writes the data to my AXI slave full block, I want exactly at the same moment my pattern counting engine to receive the data and to calculate number of occurrences of a specific pattern inside the received data. So I just connect the AXI W data port of this module to the input port of my pattern find engine. So if I look at AXI W data, I can see that AXI W data is obviously one of the input ports of this AXI slave block. Now, there's another port which is required for correct operation of my RTL, and that is the pattern in itself. As I showed you, the AXI slave light block that we have in the design is responsible for receiving the pattern from the CPU. So if I open the implementation of modified AXI slave light block, I can see that for this guy, I have added an output port which is called pattern in. And the pattern in should be, in fact, assigned a value by the CPU. So I have connected inside my AXI slave light block, I have connected the pattern in signal to one of the registers which is implemented in the AXI slave light block automatically generated by Vivado. So slave reg 0, which is actually located at the base address location of the AXI slave light block, I have connected to the pattern in. This way, when the CPU writes to slave reg 0, or better to say, when the CPU writes to the base address of this AXI slave light block, it's in fact assigning a value to pattern in. Now I go back to my AXI slave full block. The other, in fact, port that my pattern count engine has is called pattern count W, is the output, as total number of patterns that we have found. What I want to do is that I want to, in fact, store this value in a kind of memory so that later I can tell the CPU how many number of times for each of the memory locations the specific pattern has occurred. So I have defined a simple memory. I have called it pattern count. Pattern count for now has a width of 5 bits, and it has 32 elements. As I told you, we just for now our implementation supports 32 patterns. And what I do is that at the time that AXI write happens, at the time that the CPU writes some data through the AXI slave port, to this module, obviously at the same time, the pattern count will contain the number of occurrences of the pattern in the written data. At the same time, at the same clock cycle, I store the pattern count value in my pattern count array. And now I need to make the pattern count array accessible through the AXI slave clock to the CPU. So when the CPU reads from the address locations of this AXI slave clock, it should be able to practically read the pattern count value. For that purpose, obviously, what I do, I modify the RTL code that I have for my AXI slave clock so that the AXI read data port, which is practically containing the data which is being sent from AXI slave clock to the CPU when a read happens, I assign the pattern count array to AXI R data, which is the read data port of our AXI slave clock. For the address, we always use the correct number of bits from the incoming address value on the AXI address read port. Now, another functionality that I should implement is I should be able to count total number of patterns that has occurred through all of the incoming chunks of data. Obviously, when an AXI write happens, what I need to do is I need to, in fact, add the number of patterns that I have found in this written chunk of data to pattern count total. So I see that I can do that by checking if the write has happened. If this is a write to the first location of the memory, this means is the first data that CPU is writing. The pattern count total is just directly the pattern count W value itself. Otherwise, if the CPU is writing to the other locations, then you sum up the previous pattern count value with the number of pattern count that you have obtained from this write. And finally, for generating the interrupt to the CPU, I need a kind of done signal. And this done signal is generated when we see that the CPU is writing to the final location in the list of incoming data values. So as I said previously, we have 32 data chunks, and we want to do the search for 32 data chunks. So what I do is I check if a write has happened through the AXI slave port, and if the address, the write address for the write operation is equal to 31. This means that the CPU is practically writing to the final location of the array. In that case, I enable the pattern down signal. And the pattern down signal is practically an output of this module. And this signal is entering the other module, which is our AXI slave light. And now, inside my AXI slave light, I use this signal to produce the interrupt. So as I see the signal is equal to 1, as I see the signal is active, I enable the interrupt. And the interrupt will remain enabled until the CPU comes and until the CPU sees the interrupt and comes and clears the interrupt. For clearing the interrupt, I use one of the registers inside the AXI slave light block. And when I see that the CPU is writing to that register, I just clear the interrupt. So what I do is that I look if a write is happening from the CPU side. And for now, I have considered the fourth register inside the AXI slave light block as the register that is responsible for clearing the interrupt. When I see that a write is happening to that specific register, I clear the interrupt. Now, as I told you, the AXI slave light should also keep the threshold value So we have a variable, it's called threshold value, and I am using one of other slave registers which is available inside the AXI slave light for the threshold value. And then all the other thing I need to do is to generate signal out value. And for signal out, what I do is that when the done signal is coming, if the received total number of pattern counts is bigger than the threshold and signal enable is active, then the signal out is 0, otherwise always the signal out is. Then the signal out is 1, otherwise always the signal out is 0. Now I go back to the top level. The top level of the module is actually the same two AXI plugs that I showed you in the beginning, but the ports are updated. So we have a set of ports which are connecting these two AXI plugs together, and I have these two ports which are practically going to the outside world. So the ports which are in fact going to the outside world is first the interrupt is going to the CPU, then I have signal enable is an input, and then I have signal out which is an output of the module. This is the complete implementation of our IP block. So here is our updated IP component with all of the modifications that I showed you. What I see here is that our IP component, it has 4 Verilog files, in fact 3 Verilog files and 1 system Verilog file. And then here is a kind of symbolic representation of our IP block that we will see soon in more detail. And this is the kind of IP block which is ready and we can use it in our design. So now I can just begin a new project and use this IP block inside my project. Now I have created a Vivado project. Here is our block design interface open, and what I do, I come to the project settings folder, to the IP, and then I add the location that contains the IP. So here I come Vivado IP repo, and inside IP repo there's my IP. I add this folder to the repository and my IP is here. Apply, OK, and then now I add IP ZYNQ PS. I add the ZYNQ PS. Block automation. Block automation is done. Now I add the IP, so my IP, obviously it is recording time, and run connection automation, and then both of the AXI slave interfaces of my IP will be slaves for our ZYNQ PS. So here is our design up to now. They are both slaves for the ZYNQ PS, and they are being connected practically to GP0 port of the ZYNQ PS. And then I have the interrupt port which should be connected to the ZYNQ. So I double click here. The interface gets open, interrupts, fabric interrupt, and then PLPS interrupts, and then I enable this guy. And now that I have enabled this guy, I have pattern countdown interrupt that it gets connected here. Okay, and finally I have the signal out and signal enable pins of my IP, which are ports. So signal out is a port, and then the signal enable is also a port. So here my design is practically finished. What I need to do is to add suitable constraints file to this project, and the constraints file will be indicating on which pin of the FPGA the signal out will go, and from which pin of the FPGA the signal enable will come. And I have decided for signal enable to put it on one of the push buttons, and for signal out to put it on one of the LEDs. So I come here, add sources, add or create constraints, and then create file. Let's call it pins.xdc is the file that we want, and then finish. And basically what I have now is a simple text file. It's called pins.xdc, and it should be filled up with suitable constraints comments. Practically, the constraint file that I'm talking about contains 2 lines. This is one line, and this is another line for the constraint file, and for now the rest of them are commented out. One line is connecting the signal out to LED's 8-bit try O bit 0, and the other one is connecting the signal enable to push button 5 bits try input. And this is all you need for connecting your signal out and signal in to suitable interfaces of your Z board. In fact, the definition file for Z board is already defining where on which pin this port is going to be placed. So all you need to, in fact, indicate is I'm going to put signal out on LED pins and signal enable on push button pins. This is the constraint file that I need. Furthermore, for my tests, for now I don't want to write any software on the SDK. What I do to check the interrupt, I use, in fact, the ILAs, and I capture the interrupt signal over the FPGA using the ILA core as I described in previous sessions, and I watch it inside the, in fact, waveform viewers of Vivado. And I have done that before, so I have another file, another constraint file, which contains the definitions for adding the interrupt signal to the list of signals which is being monitored by the ILA core. So here is my design. I am practically capturing this signal, the interrupt signal. I have put this signal out and signal enable on suitable ports on the board, and I have my IP designed with all of the specification that we talked about, and we can in fact try this on the real hardware. So here I have my Z board. I can turn it on right now, and then what I can do, in fact, through my command prompt, I can program this guy. So I have created previously a set of TCL files containing suitable commands for programming the guy. So I have here, if I vim init.dcl, this is the first file I'm going to run. It's basically, you know, everything in this file is connecting to the ARM hardware debugger. It's sourcing the PS_7 init, and then it runs PS7_ init and PS7 post config. And I have previously described in detail the functionality of all of these commands. So what I do, I say xmd, and then I say source init.tcl. And that is it. The initialization is done, and I come here to the Vivado environment and open hardware manager, open target, and then I program, in fact, my ZYNQ device. As you program the ZYNQ device, since you have a signal which you are monitoring using the ILA core, this interface related to, in fact, watching the signals which are being captured over the FPGA also gets open. And now, if I just capture all of the waveforms that I have connected to ILA, I have one signal connected to the ILA core. It's called pattern count interrupt, as you see here. It's one of the most difficult tasks in the world to, in fact, align these bars, and I have always this problem with Vivado. You very hardly can really align this line with, especially if you are using a notebook. Either you can't align it, or if you can align it, it takes 10 years. Okay, anyway, this is our waveform interface. This is a signal that we are capturing, and right now it's all 0, obviously, because we have not written any data to our module, and our module has not done anything. What I do is that I want to define a trigger for this signal, and the trigger that I define is like the following. I want the capture core to kind of start triggering when the signal gets 1 from 0. And then the trigger window, in fact, for showing to the user, I want the trigger event to be placed at sample number 200. So it want it to be placed kind of in the middle of the waveform window, so that I can see what has been happening before and what's happening after. So trigger position in window I set to 200, total number of samples I'm capturing 1024. This is the trigger, and I put the ILA core in trigger mode, so it's now waiting for trigger. And now obviously I can come back to my XMD interface, and here I can test and see if the core, I can really talk to the core. I can write patterns to the core, and I can check if the core is really counting the number of patterns in the data chunks. So if I go back and open the block design here, in the block design, obviously each of these AXI slave ports that my IP has, each of these AXI slave blocks, the full AXI slave block and the light AXI slave block, each of these guys has a base address. The base address is obviously here in the address editor. So for the AXI light interface, I have the base address of 43C0 all 0, and for the other one, I have the base address of 4AA0 all 0. So this is the guy that is containing the pattern count engine, and when I write to different locations of it, for each location it counts the number of that specific pattern which has happened, and this is the guy which contains all of those configuration registers. So the first thing I should do, I should define the pattern that I want the search to happen for. And if I go back and look at the implementation of the RTL, of the code, if I look at S00, basically the AXI light interface, I want to see which address I have used for pattern in. I select pattern in, I scroll through the code that I have, and here pattern in is equal to slave reg 0. This means that by writing directly to the base address 43C00000, I can define the pattern that I want. Okay, so 43C000. This is the pattern. So the pattern you have defined, and now by writing to this address, in fact you are sending the chunks of data for which the search should happen. For example, if I write this number to this address, now if I read back this address, according to my implementation, what I receive should be the number of occurrences of this pattern in this data chunk. So if I say MRD 0AA blah blah blah, then it's containing the number of occurrences of the 5 pattern in 5555. Obviously, when you have 5555, you have more occurrences than just 4, because there are also in between the pattern is happening. So the pattern search engine is working, and now I can continue writing data to other locations of the memory of my AXI full block. So I can check the correct operation of my module by writing, in fact, to the base address of my AXI slave full block. That address contains the memory that when I write data to that memory, locations of that memory will be, in fact, forwarded to the pattern search engine, and the pattern search engine counts the number of occurrences of the specific pattern for each location and stores it in another memory, as I showed you in the implementation. So let's here write to the base address of the AXI slave full block, this number. And previously, I have defined the search pattern as this number. And now, if I read back exactly the same location, I should see number of occurrences of 5101 in this pattern. So MRD, this is the number of occurrences. Once more, I go back to the RTL implementation of the code to see what's really happening. When I am writing the data through the AXI by the CPU to this address through the AXI slave full block, when I am writing the data, what's happening? Practically, this piece of code is being executed because this condition comes true. A write is happening to my AXI slave. And so this condition is true by this positive clock edge, so this line of code will be executed. And this is a small memory I have implemented in my AXI slave full block, and this small memory is responsible for keeping number of occurrences of the pattern in the current received chunk of data. Why? Because I have connected the write data port of this AXI slave full block to my pattern count engine. So as the write is happening from the CPU to my AXI slave full block, the CPU is putting this number on this port, and since it is a completely combinational block in the same clock cycle, here I will have the correct number of occurrences of that pattern, of this pattern in the incoming data, and then with the incoming positive edge of the clock, this value will be stored here. And when you read this value by the CPU, practically this piece of code will be executed and the contents of the array will be copied to the R data port of the AXI interface, and this is what you see. So when I write to this address, I'm transferring the chunk of data for which I want the search operation to happen, and when I'm reading from the same address, practically what I am reading is the number of occurrences of the specifically defined pattern in the chunk of data. Now let's extend our, in fact, test. So I write to another location in the memory of my AXI slave full block. For example, I write, for example, this number. And again, if I read, obviously, I will read to the number of occurrences of the pattern inside this chunk of data from the same address. And now, if I read total number of occurrences, so I want to know in total how many number of times that specific pattern has happened in my total array that I have inside the AXI slave block. But for reading that variable, if I look at the implementation, I can see that the pattern count total will be reflected to the CPU by the AXI slave light interface and through, in fact, the second register that I have inside my AXI slave light interface. So in order to read total number of occurrences of the pattern, I should read the AXI slave light, its second register. So this is total number of occurrences of the patterns inside all of the array that I have. Now let's go back to Vivado. Vivado, if I in fact come back to program and debug, I can see that my ILA core is still in waiting for trigger. In fact, no interrupt has happened yet. Because as of the code that I have written, the interrupt will happen if I come back to my AXI slave full block. When does the interrupt happen? The interrupt happens when the pattern countdown goes active. And when does the pattern countdown goes active? It goes active when I write to the final chunk of data in the array that I have in my AXI slave full block. And that is the address location 31. So if I write to the address location 31 of my AXI slave full block, I expect the interrupt to happen. And that is the address location, if I recall correctly, is async. So I write just the value here. No, this address location. So let's first calculate what is the address location corresponding to this specific chunk number 31 inside my AXI slave full block. Chunk number 31 multiplied by 4, and then I should convert it into a hexadecimal value. So I bring a simple calculator, and 31 multiplied by 4, and then please convert it into hexadecimal is 7C. So what I do here, I expect that if I write to 4AA0, then 007C, a value. If I press enter, if I do that, if I press enter, I expect the waiting for trigger to go to idle. Because practically what's happening is that this chunk of code will be executed. We are writing to the final member of the array, and as we do that, the pattern countdown goes active, and inside the AXI slave light, if the pattern countdown goes active, what is going to happen is that I'm going to generate the interrupt. Okay, so I come back Vivado, I bring the text. Okay, so what is happening is that from waiting for trigger, we go to idle, and if I look at my waveform, I can see that the interrupt has been 0 so far, and since then it is 1. And now if I just capture whatever there is on the interrupt line, I can capture that by pressing this button, and now for interrupt line is always 1. Obviously interrupt line stays 1 until the CPU goes and clear the interrupt. And how it will be happening, according to the implementation that we have created, we have assigned one of the registers that we have on the AXI slave light interface for this purpose. The register number 3 we have assigned for this purpose. So obviously, as the CPU, if I perform a write operation to 43C0 and then register 3. Register 3 will be obviously corresponding to address C. Register 0 is address 0, register 1 address 4, register 2 address 8, and this one should be address C. So 0, 0, 0 and C, and whatever value I write there, I expect to see that the interrupt comes down. So I write a value, I capture the value of the interrupt, and now I see that the interrupt is 0. So our module functionality is there, it's working, and we are seeing it with our XMD interface. Obviously, I didn't use the software, I didn't develop any software to test the functionality of the module, but all of the things that you can do through the software, we can also do here through XMD, and it's usually a very good idea. So once you create your IP, for initial tests, it's a good idea to, in fact, perform some basic read writes to your module through XMD and to see if the basic functionality is there. Okay, so what we did through this lesson, we briefly had an overview on the signals of AXI slave interfaces. We compared AXI slave full, AXI slave light interfaces. And then we developed a sample hardware accelerator that was responsible for performing a kind of acceleration task that can be used for database applications. It was a very simple accelerator, and as you saw, the development, the creation of the RTL is not that difficult, but at the same time, it is not that easy. The example design is there along with the video on the website of Microelectronic System Design Research Group. So I encourage you to grab the source code of this example design and look at them for yourself. The message that I want to convey to you is that, in fact, coding in RTL is not that difficult and is not that scary, it's not complicated, and you can really annotate the code which is already being automatically generated by the Vivado yourself and add your own custom functionality to the design. That's the end of this video. I would like to thank all of the people who are involved in producing and editing these videos, and we will continue in the next session with AXI master interfacing. Thanks for watching. Bye.